This machine costs $400 million. Its job is to hit a microscopic tin droplet with a laser 3 times in a row within 20 microseconds, while the droplet is moving at 250 kilometers per hour. For 50 years, the tech industry has lived by a single pattern, Moore's Law. It's the observation that we can double our computing power every 2 years by making transistors smaller and smaller. Intel co-founder Gordon Moore first identified this trend in 1965, and it has since become the primary driver of the digital economy. Printing these chips requires photolithography, a process of shining light through a patterned mask to etch microscopic designs into silicon. But in the late 1990s, that growth slowed. To print features any smaller, the industry needed shorter wavelengths of light, and they had reached the physical limit of their existing deep UV technology. The only way forward was a transition to extreme ultraviolet light, or EUV. These wavelengths are so short they behave more like X-rays. However, EUV light has a major catch. It is absorbed by almost everything. It cannot travel through air, and it cannot pass through the glass lenses used to focus it. By the turn of the millennium, the consensus was clear. Harnessing EUV was physically impossible. If it couldn't be done, Moore's Law and the exponential growth of technology would effectively end. In the 1980s, Hiro Kinoshita and Andy Howerlook proposed a system to use EUV light. At conferences, their colleagues laughed at the idea. The skeptics had a point. Their proposal required building an artificial sun in a total vacuum, all without the use of a single traditional lens. To solve the lens problem, Kinoshita and Howerlook looked to curved mirrors. Instead of letting light pass through glass, they would bounce the EUV waves to focus them. These mirrors are engineered at the atomic level. Alternating layers of tungsten and carbon force EUV light to reflect constructively instead of being absorbed. The stack requires exactly 76 layers, tuned to 1/4 of the wavelength. Still, they reflect a tiny fraction of light. Because EUV wavelengths are so small, the mirror surfaces have to be atomically smooth. Any microscopic bump would scatter the light randomly, ruining the image. If you took one of these mirrors and scaled it to the size of the entire Earth, the largest bump on its surface would be no thicker than a single playing card. As American companies abandoned the technology, a Dutch firm called ASML took over the effort to commercialize EUV. To generate enough light for mass production, ASML engineers had to create a 220,000-degree plasma by blasting molten tin with a high-powered CO2 laser. The timing is incredibly tight. The laser must hit 50,000 individual droplets every single second, without missing once. This process creates a massive amount of debris. If even a few atoms of vaporized tin landed on the mirrors, those $400 million machines would be permanently ruined. To minimize debris, the system uses a 2-step strike. A pre-pulse laser hits the droplet first, flattening the sphere into a pancake. The main laser then vaporizes the tin more efficiently. Finally, a hurricane-speed stream of hydrogen gas sweeps remaining particles away from the optics. By managing 50,000 of these miniature explosions every second inside a hydrogen storm, engineers finally turned EUV into a manufacturing tool. By 2016, ASML began shipping the completed machines. Each one is the size of a bus and requires 7 Boeing 747s to transport. Inside, components move at 20 Gs of acceleration, yet the machine can align multiple chip layers with a precision of 5 silicon atoms. This is the technology currently printing the chips inside your smartphone and your computer. It took 30 years to reach this point. If Hiro Kinoshita or the team at ASML had accepted the standard belief that EUV was impossible, this entire ecosystem simply would not exist. It is a reminder that technological progress relies on people who look at a physical limit and simply refuse to accept it.